All right, so this is the basic ADCS control systems. It's a very straightforward closed loop system. We see the guidance subsystem block here that generates the desired attitude, which will be the input that will go into the attitude error generator block. So yeah, that's basically the desired attitude that we want the system to have. And then this error generator block receives this attitude from the onboard computer ground station, again in the guidance subsystem block, and also the equations, direction, cosine matrix, or any other orientation representation. It calculates the error signal for the attitude controller subsystem. So it's very important, these two different inputs, the desired and the current attitude. And then it will go into the attitude controller subsystems, as we see here. And of course, we'll send the control signals into the actuators, so they will produce the necessary torque to rotate the direction of our satellite or plant. We also see here a block of disturbances, torque disturbances, that will also affect the satellite, that we'll need to take into account when calculating the satellite equations. These equations will produce the satellite states, which will be fed as input into the navigation subsystem block, and this will output, the current satellite's attitude, which will go again into as a feedback into the input to compare it with the desired attitude. Okay, next slide. Okay, so this is, I'm going to span a little bit more into each subsystem. This is the guidance subsystem. It performs two main tasks for the ADCS. The first is to receive and analyze the target attitude or its rate from satellite ground station. The target attitude depends on several factors, such as orbital position of the satellite, epoch, satellite attitude rate, etc. The second task that the guidance system should perform is to generate a sequence of target attitude for the attitude controller. This could be generated using various methods, such as quaternion interpolation, Euler angles interpolation, axis angle rotation, direction cosine matrix error, and these are very different methods. And the output of this subsystem will be used as basically a set point for the attitude controller. Okay, next slide. Okay, so this is the attitude controller subsystem, which receives the attitude error signal from the error generator block, and by using control techniques such as, we see here a little bit, some examples like the PID control, nonlinear control, model predictive control. Also, there's other type of controls that we could go into, like artificial neural networks, optimal controller, facile controller, etc. It determines how each actuator should work. To achieve this purpose, first, this subsystem should calculate the required torque for the satellite to be able to follow the target attitude. And second, it should convert the calculated torque to an equivalent input signal for each actuator. The actuator being the reaction wheel and the magnetorquer. For example, this subsystem should provide the required angular rate and acceleration for the reaction wheel in order to create the required torque. For this purpose, this subsystem should include a dynamic model of each actuator, because it varies with time, not a static model. So furthermore, this subsystem should have a torque allocation algorithm in order to have a better performance and efficiency. Okay, the next slide. Okay, so we see here the actuator subsystems, which is, it receives its command from the attitude controller subsystem and will generate the required torque for the satellite to follow the desired attitude. We see here that the reaction wheels and the magnetorquer complementing each other and generating the necessary torque, to rotate our satellite in the direction that we will want. Okay, next slide. Okay, so this is the satellite subsystem. The main equations that we will be used for dynamic simulations are Euler-Newton equations. These equations will be used along with kinematic simulations of the satellite. The kinematic simulations will provide orientation states of the satellite using orientation differential equations. This subsystem contains a 6 degrees of freedom model, or maybe a 3 degrees of freedom model. It depends on the requirements based on the mission of the satellite. This subsystem will also simulate the satellite's orientation using mechanical parameters and mass properties like the moments of inertia, the mass, the center of mass, etc. It's worth noting that this subsystem is only required during the design and testing of the ADCS using simulation techniques, and obviously in a real flight. The actual satellite will represent this subsystem. Okay, next slide. Okay, so we see here the navigation subsystem. This subsystem aims to calculate and provide an estimation of the satellite's orientation with respect to Earth, Sun, or any other reference points that we have on space, such as stars too. The estimated attitude will be used as input for the guidance and controllers subsystems. It's made up of the IMU and the attitude estimator block. As we see here, the raw data from the IMU consisting of the gyroscope, accelerometer, and the magnetometer, which are all 3 axes, along with the sun sensor and the GPS data, will be passed to the attitude estimator block. Okay, now this attitude estimator block uses several estimation techniques, such as the Kalman filter, the data fusion algorithm to combine different data inputs, and the noise reduction techniques to reduce the measurement noise coming from the sensors and all the measuring devices, in order to calculate an accurate attitude. Okay, next slide. Okay, so this is the torque block. So to examine the performance of the ADCS, it's necessary to investigate the effects of the environmental disturbances on the satellite attitude. So we see here that there are 4 main torque disturbances that act on the satellite orbiting on the Earth. The first one is the aerodynamics torque. This torque is due to the air density, and it has significant effect on LEO satellites because the LEO satellites will orbit in a very low orbit, So you also have the gravity gradient torque. This torque is created due to the difference Earth gravity field, and usually should be taken into consideration for LEO satellites. However, the magnitude of this torque is very small compared to the aerodynamics torque, or smaller. Also, we have the Earth magnetic torque. Basically, the Earth's magnetic field sensed by the satellite is going to vary, while the satellite is orbiting the Earth. So this magnetic field creates a torque that could affect the orientation of the satellite. And lastly, we have the solar radiation pressure torque. The solar radiation pressure varies with time and could affect the orientation of the satellite. So this subsystem will produce an output, as the environmental disturbances that will go into the satellite block.